This presentation covers the concept of disconnecting directly connected impervious area, commonly referred to as DCIA, and how to calculate maximum soil storage when impervious runoff is redirected onto an adjacent pervious area. Disconnecting impervious surfaces from the storm drainage system is a widely used green infrastructure strategy that helps reduce annual runoff volumes and pollutant loads. Getting the calculations right is essential to realizing the full benefits of this approach, and this material has been updated as of April 2026 to reflect maximum soil storage methods within the BMPFast framework. This presentation covers several key topics: what the directly connected impervious area, or DCIA, actually is, how to calculate it, and how it applies to a real example project. A central concept here is the maximum soil storage value, referred to as S'. This value defines the upper limit of how much runoff a soil area can absorb before it overflows. We calculate S' using the formula S' equals 1000 divided by the curve number, minus 10. The curve number, or CN, is a measure of how permeable and absorbent the soil and land cover are. To put this in practical terms, when the CN is 50, indicating relatively permeable soil, the maximum storage S' is 10 inches. But when the CN rises to 78, reflecting denser or more compacted soil conditions, S' drops to just 2.8 inches. So the higher the curve number, the less storage capacity the soil has. The fundamental question we are trying to answer is whether the soil storage area receiving runoff from adjacent impervious surfaces can actually hold that runoff during a 3-year 1-hour rain event without overflowing. For this analysis, we use a storm depth of 2.4 inches. The total volume the soil must handle includes both the runoff flowing in from the adjacent impervious area and the direct rainfall falling onto the soil storage area itself. In the example project, the area being disconnected from the drainage system is the adjacent impervious area, and determining whether that disconnection is effective depends entirely on whether S' is large enough to handle the combined load. The Applicant's Handbook, Volume 1, from June 2024, gives us a precise definition of directly connected impervious area, commonly referred to as DCIA. This includes buildings, impermeable pavement, and any other impervious surfaces that drain directly into a conveyance system without first flowing across sufficient permeable vegetated land. The key idea here is that word directly. The runoff goes straight into a pipe or channel without any opportunity to infiltrate into the ground first. When we can disconnect part of that DCIA, we reduce both the annual volume of runoff and the associated pollutant loading. That disconnection has real water quality and water quantity benefits. So how do we determine whether an impervious area is actually disconnected? Section 9.2 of the handbook gives us the technical standard. An area qualifies as non-DCIA if the runoff flows over at least 10 feet of undisturbed pervious area where the soils are hydrologic soil group A or B. Those are your sandier, more permeable soils. For all other soil types, the required flow length increases to at least 20 feet of undisturbed pervious area. There is also an alternative path for applicants. If the standard width cannot be achieved, the applicant can demonstrate that a narrower width still provides sufficient infiltration by percolating the runoff volume generated from a 3-year 1-hour storm event. That storm event is typically associated with a rainfall depth greater than 2 inches, representing a meaningful design storm for evaluating whether true hydrologic disconnection is occurring. Capturing the runoff from a 3-year 1-hour rain event produces an annual capture effectiveness of at least 95% for most land uses. This holds true when the rainfall depth is around 2.2 to 2.4 inches, provided the soils have sufficient storage capacity remaining to receive the runoff. For HSGA soils, which are sandy soils with excellent infiltration characteristics, the potential storage is quite significant. Using the curve number method, the maximum soil storage S is calculated as 1000 divided by the curve number, minus 10. For an A soil with a curve number of 50, that gives a storage capacity of 10 inches. For a C soil with a curve number of 78, the storage capacity is only about 2.82 inches. So soils can store far more water than sea soils. Now the practical question is, how wide does an impervious overland flow area need to be in order to drain into a 10-foot wide strip of HSGA soil and have all the runoff infiltrate? Setting up a simple water balance, the runoff from the impervious area, which generates the full 2.4 inches of rainfall as runoff, must equal the available storage in the 10-foot soil strip after accounting for the rain that falls directly on it. Working through that equation, the answer comes out to 32 feet. So a 32-foot wide impervious surface draining into a 10-foot wide soil strip will achieve full infiltration for the 3-year, 1-hour design storm. It is worth noting that 10 feet is specifically referenced in Section 9.2 of the applicant's handbook, making this a practically relevant calculation. As an exercise, you can apply this same approach to different curve number values to understand how soil type affects the required dimensions of your treatment area. Let's walk through an example project focused on disconnecting directly connected impervious area, or DCIA. The first step is to enter the general site information for the project. Once you're in this section, you'll notice that the Enter Catchment button is the only one that is active and lit up. This is by design, because the tool cannot perform any annual removal analysis until the catchment data has been provided first. You'll also notice yellow information buttons throughout the interface. These buttons provide additional details about the drop-down menu items and offer general help, which is especially useful if you haven't gone through some of the other learning modules in this series. When calculating whether a soil storage area can handle the runoff from a 3-year, 1-hour storm event, we need to account for 2 sources of water coming into that area. First, there is the runoff generated from an adjacent impervious area, and second, there is the rainfall falling directly onto the soil storage area itself. The maximum storage capacity of the soil area is calculated by multiplying S prime, which represents the maximum soil storage in inches derived from the curve number, by the storage area in acres, then dividing by 12 to convert inches to feet and get the result in acre feet. To determine whether that storage is sufficient, we compare it against the total water volume the area must receive. That total includes the runoff from the adjacent area, calculated as the 3-year 1-hour rainfall depth multiplied by the adjacent area acreage divided by 12, plus the rainfall landing directly on the soil storage area, calculated the same way using the storage area acreage. So the key question becomes, is S prime times the storage area greater than or equal to the 3-year 1-hour rainfall times the sum of both the adjacent area and the storage area? If the soil storage area cannot accommodate all of that water, then either the overall site runoff calculations need to be adjusted or the size of the adjacent contributing area needs to be reduced. It is also important to note that there is no storage capacity beneath pervious pavement itself, so all of the storage must come from the soil storage area. Working through the watershed characteristics for this design, we start with a proposed impervious area of 1.3 acres, of which 1.1 acres will be disconnected. That leaves only 0.2 acres as directly connected impervious area, which represents 10% of the total 2.0 acre catchment. The soil type here is hydrologic soil group A, which has a curve number of 50. The pervious area is calculated as the total area minus the impervious area, giving us 0.7 acres. With a curve number of 50, the maximum storage capacity works out to 10 inches, using the standard formula of 1,000 divided by the curve number, minus 10. After subtracting the retention area of 0.02 acres, the effective pervious area becomes 0.68 acres. An important point here is that we are not calculating a composite curve number. The reason is that there is no storage beneath the impervious pavement itself, so that area contributes nothing to infiltration or storage capacity. Only the pervious soil area counts. Now we check whether that pervious area can actually handle the runoff from the 1.1 acres of disconnected impervious area plus the rainfall falling directly onto it. The calculation is 0.68 acres times 10 inches of storage, minus 1.1 acres times 2.4 inches of runoff, minus 0.68 acres times 2.4 inches of runoff from the pervious area itself. That gives us 6.8 minus 2.64 minus 1.63, which equals a storage residual of 2.53 acre inches. Since that value is positive, storage is not exceeded, and disconnecting the 1.1 acres of impervious area is a viable approach with sufficient soil storage capacity to manage the redirected runoff. This example looks at a rain garden that incorporates sorption media specifically designed to protect the groundwater, and the site has a hydrologic soil group A soil classification, which indicates highly permeable, well-drained soils, with the addition of bold and gold media installed at 24 inches deep. The system uses 1,300 cubic feet of that sorption media, along with 2,600 cubic feet of water storage above the media. That combination is what allows this design to meet the performance standards while also safeguarding groundwater quality. The results here are strong. The rain garden achieves an average annual pollutant removal of 80.2%, which exceeds both the specified removal thresholds and the net improvement requirements. Specifically, the design meets the performance standard for total nitrogen at a net improvement of 63.1% and for total phosphorus at 60.9%. So not only does this configuration protect the groundwater through the sorption media, it also delivers meaningful pollutant reduction that satisfies the regulatory benchmarks for this 0.20 acre site. When working with any stormwater modeling software, one of the most important steps is properly configuring your catchments. You need to define how runoff water flows from one catchment to another, because that drainage pathway drives the entire analysis. When using BMPFast specifically, the configuration process also involves selecting your best management practice, or BMP. One important feature to be aware of is the multiple BMP selection option. This allows you to place several BMPs in series within a single catchment, meaning the runoff passes through one BMP and then another in sequence before leaving the catchment. Getting this configuration right is essential for accurately modeling how your BMPs will perform together. When we disconnect the directly connected impervious area, we see significant reductions in both discharge volume and pollutant mass. In this scenario, we are disconnecting 1.1 acres of the 1.3 acre directly connected impervious area and routing that runoff through a rain garden designed with an HSG-A soil, which corresponds to a curve number of 50. The results are striking. Without any disconnection or best management practice in place, the post-condition runoff volume is 22 inches per year. After disconnecting and implementing the rain garden, that volume drops to just 5.30 inches per year. That is a dramatic reduction, and it demonstrates how effective disconnection can be when paired with an appropriate best management practice. On the water quality side, the discharge of total nitrogen comes out to 0.156 pounds per year, and total phosphorus comes out to 0.84 pounds per year. These values represent the load leaving the site after the best management practice has done its work. Importantly, both the specified percentage reduction requirement and the net improvement criteria are met with this approach. That means this design is not only reducing volume, it is also achieving the performance standards required for pollutant load reduction, disconnecting impervious area, and directing runoff to a properly designed rain garden with favorable soil conditions is a powerful and effective strategy for meeting stormwater management goals. Here we have a concrete example showing what happens when you disconnect 1.1 acres out of 1.3 acres of directly connected impervious area in Type A soils, and how that compares to keeping the DCIA connected versus adding a best management practice on top of disconnection. Looking at the numbers, when you keep the DCIA connected with no BMPs at all, you are generating 3.666 acre-feet of runoff per year, which works out to 22 inches annually. That comes with 17.64 pounds per year of total nitrogen and 3.259 pounds per year of total phosphorus discharging from the site. Those are significant loads. Now, when you disconnect that DCIA, the transformation is dramatic. Runoff drops to 0.884 acre-feet per year, and nitrogen loading falls to just over 4.25 pounds per year. That is a reduction of roughly 75% simply by disconnecting the impervious area and allowing runoff to flow across pervious surfaces rather than directly into the stormwater system. When you go one step further and add a retention BMP to the disconnected system, the numbers drop even further, down to 0.175 acre-feet of runoff and just 0.84 pounds of total nitrogen per year. That is the column marked with the asterisk, meaning all output measures with BMPs meet the Environmental Resource Permitting Performance Standard for that site. The key takeaway here is that disconnection alone can be powerful enough to meet a loading target in certain regulatory contexts, such as a basin management action plan. If the disconnection by itself brings you to your required discharge load, you may not need any additional BMP, but combining disconnection with a retention BMP gives you the greatest reduction in both volume and pollutant loading. To wrap up, let's review what we covered in this module. One of the most important takeaways is understanding the role that directly connected impervious area, or DCIA, plays in protecting water quality. When impervious surfaces drain directly to a water body or conveyance system without any opportunity for infiltration or storage, the volume and pollutant load of that runoff increases significantly. Disconnecting DCIA by routing overland flow from impervious areas across pervious areas is an effective way to reduce both runoff volumes and pollutant loadings. We also looked at how to determine the appropriate amount of pervious area needed to achieve that disconnection. As a general rule for Type A soils, about 10 feet of overland flow across a pervious area is sufficient to disconnect DCIA. For example, using a curve number of 50 and a 10-foot wide pervious strip, the runoff generated from a 32-foot wide impervious area can be fully stored within that pervious zone. We also covered the importance of accounting for maximum soil storage capacity, particularly when multiple adjacent areas are all draining to the same soil storage zone, since that storage can become exhausted quickly. The example project we walked through was designed to help you apply these calculation methods to your own similar analyses. And remember, beyond meeting ERP performance standards, you may also need to evaluate surface discharge in terms of both mass and volume, depending on the requirements of your specific project. Thank you for watching, and we hope this module gives you a strong foundation for applying these concepts in your stormwater design work. That brings us to the end of this presentation on disconnecting the directly connected impervious area, or DCIA, using BMPFast. This module has covered the concepts and methods you need to evaluate a disconnected impervious area, and you are encouraged to review other learning modules as needed and apply to take the competency test. For more details on assessment, see the learning module called Self-Test. Thank you for viewing and listening to this information.